Out past the orbit of the planets, there is a giant invisible shield that helps make life possible here on Earth. This is the heliosphere.
The heliosphere is our home in the universe. We wouldn't be here without it. Our solar system is surrounded by a protective bubble that is created by the solar wind, a constant stream of particles that is being released by the sun's atmosphere and is blowing constantly outwards and protects us from harsh galactic radiation.
The heliosphere is always around us, but it's constantly changing. That's because the sun's activity changes on a natural 11-year cycle, as well as with shorter-term variations. As the solar wind fluctuates, the heliosphere responds.
You can think of having a balloon and it actually expands when the sun's more active and there's more solar wind. And when the sun's quiet, it contracts. And that changes how damaging particles from the distant galaxy get into our solar system.
At around 11 billion miles from Earth to its closest edge, the boundary of the heliosphere is hard to study. Despite its importance to life on Earth, only a couple of spacecraft have flown through its boundaries, and comprehensive measurements of the entire heliosphere are limited. But that's changing with NASA's Interstellar Mapping and Acceleration Probe mission, or IMAP. As a modern-day celestial cartographer, IMAP will fill in the blank spots on the map of the heliosphere and help us understand the fundamental processes happening across our solar system.
IMAP will chart everything from the particles coming out from the sun to the material coming in from interstellar space, allowing us to make measurements which are 30 times more sensitive and higher resolution than we're currently able to do, and give us a very fine picture of what's going on out there.
IMAP is an amazing mission because it's got 10 instruments that measure energetic particles from low energy all the way up to high energy, things that are moving at close to the speed of light.
The spacecraft will be stationed at Lagrange Point 1, or L1, a location approximately 1 million miles from Earth toward the Sun. From that vantage point, IMAP will study our heliosphere in 3 main ways. First, IMAP will map the boundary of the heliosphere using special atomic messengers known as energetic neutral atoms, or ENAs. These largely start as normal, electrically charged solar wind particles traveling out from the sun. Like all charged particles, these solar wind particles spiral around magnetic field lines in space, like a roller coaster on a track. Eventually, the particles reach the boundary of the heliosphere, where they crash into others from interstellar space. When they collide, they become neutral, meaning they no longer have an electrical charge, and transform into ENAs. As a result, the particles are no longer bound by magnetic fields. This allows them to move in straight lines.
That energetic neutral atom, the ENA, is free of the magnetic field. It's not trapped anymore, so it's free to travel all the way back to Earth.
That's useful because you can actually trace back where they came from. And that's not true of electrically charged particles. Energetic neutral atoms let us map out where these interactions are happening out at the edge of our solar system.
IMAP will use this data to create maps of our dynamic heliosphere.
Second, IMAP will measure tiny particles within the heliosphere, including some from interstellar dust, the leftovers of supernova explosions. Studying these interstellar particles will give us a better understanding of the material floating between stars and give clues about our solar system's infancy.
We'll be able to capture about 200 of those particles in the first 2 years of the mission, which is many more particles than we have ever been able to measure before.
Third, IMAP will measure the source of the heliosphere, the solar wind, in real time. High-energy particles from the sun can produce hazardous conditions for satellites and astronauts, as well as power grids and infrastructure on Earth. Measurements from IMAP will help us better prepare for dangerous solar particles and radiation that are headed toward our planet.
IMAP patrols around a point about 30 to 40 minutes closer to the sun than the Earth is. And so as the solar wind comes out, it passes over the IMAP spacecraft and allows us to give advanced warning of what's going on before that affects the Earth.
This information will be essential for the future of human exploration as astronauts venture beyond Earth to the Moon and Mars. IMAP's measurements will give scientists a more complete look at our home in space than ever before. The mission will help us learn not just about our heliosphere, but also about similar bubbles around other stars, called astrospheres, as we search for life across the universe.
The heliosphere is the only astrosphere we can study up close, and in fact is the only habitable atmosphere we know of, so far anyway. So if we want to study other astrospheres and whether they have habitable exoplanets, we need to understand how our own home in the galaxy was created.
What makes me most excited about IMAP is what we haven't even thought of yet, the new discoveries, the new inventions, the new material that will come out of the mission. IMAP is helping us unlock the unknown.